Okay, so today then we're going to do some randomized algorithms for the first time. So last Thursday we did amortized analysis, and then today we'll do a little bit of randomized analysis. And I think I'm going to follow up with one more lecture on each, sort of like some topic using amortized, one topic using randomized. So today will be a little more about basics. This also coincides with roughly the first lecture of the randomized class, in case you're interested. I'll give you some preview. So, okay, but this is all falling, the last section of our class is about this average case analysis in a very specific sense of the word average. So amortized was about kind of average running time in hindsight, finding ways to charge so that it looked like it was behaving in such and such a way the whole time. And then today we'll have randomized algorithms that deliberately inject some randomness. They flip some coins. They find it advantageous for some reason to flip coins. And then we're going to be averaging over these random outcomes. Okay. But what's really important to point out is that we're still assuming worst case inputs and still doing a worst case analysis. But we're doing kind of average in the worst case. Okay. Um, right. So, okay. So stuff we'll do today. We'll have to go over, first of all, have you guys been exposed to some probability before in discrete math? Uh, has it been a while? 'Cause I mean, I typically go over definitions again, but if it gets too boring, you should let me know. Um, but there's some definitions we'll need, but then we'll get to analyze three fun algorithms. One is for three sat. Actually, I think we've discussed this a little bit in class. Another is quicksort. That's a classic. And then I'm not going to actually go over the algorithm for I'm not going to go over the analysis for quick select. I'm going to just present the algorithm and then see if you can kind of recover the analysis for homework. Because in some ways it's similar to quicksort, but some changes need to be made. But this way you can kind of practice what you learned. Okay, so good. Okay, so let's start. What I'm going to do first is I'm going to present the three algorithms because they're kind of fun and exciting. And then we'll go through all the definitions. But if it's boring, you just tell me and I'll be happy to skip through them. And then we'll go back and discuss these algorithms in detail. So, okay, three sat, we've been doing this for a little while, so you're used to this. You get some CNF formulas, three variables per clause. Yeah. And as we know, this is like almost the number one MP complete problem, right? So we don't think you're going to be able to solve things in any general way. Okay. So then, if we can't get an exact algorithm, then you might ask, okay, can we still try to do as well as possible? Okay. So, max 3 sat, we've done max 2 sat. So here you're just trying to satisfy as many clauses as possible. But the nice thing about this version of the problem, you're just trying to do as well as you can, is that it makes more sense compared to the all or nothing uh, to consider approximation algorithms. Okay? So you get some formula, and who knows what the best you can do is. It's MP hard to figure out the best you can do. But can you guarantee that you're within a factor of 2 of the best possible, et cetera, et cetera? Okay, so one way out of these MP complete problems that we can't solve exactly is try to get an approximate solution instead, right? Getting an approximate solution doesn't prove P equals NP at all, right? It's not going to help you solve an exact formula, but it can still be very practical. Okay, so so the key point is that it doesn't violate any rules of the universe to get a good approximation for SAT. Okay, so any ideas for how to approximate SAT? I know we might have discussed this a little bit, but maybe you forgot. Maybe you never noticed. So I give you a SAT formula, and your goal is to just satisfy as many as possible. Yeah, I give you three SAT. Yeah. Okay. So that's exactly what we'll do. I'll only mention that sometimes students want to say, well, for each variable, let me figure out if it satisfies more clauses by taking or not. right? Or there's various other strategies and kind of greedy heuristics you can try to do. Yeah, we usually have a longer discussion, but today we're going to cut to the chase. So here's maybe the silliest approximation algorithm, right? The silliest algorithm I can think of. There's n variables, and I'll go through them one by one. And for each one, oh, up in there, right? I'm going to randomly set xi to be true with probability 1/2, false with probability 1/2. Good. So we're going to do two things. We're going to first prove that this will get you a 7/8 approximation. That'll be kind of our first analysis together. So it's not supposed to be too complicated, but hopefully you'll learn something. The second part you maybe haven't seen before, we're going to take that silly algorithm, which is about as random as you can expect. Like every choice was random. It didn't even look at the formula, right? This is an absurd algorithm. And we're going to make it deterministic. So that'll be a little more subtle. What's sort of amazing about all this, we won't prove this today, is that you can't do better than 7/8. Okay? If you can get 7/8 plus 0.00001, then you'll prove that P equals NP. Okay, so that's what this PCP theorem says. All right, this is an amazing thing because 7/8 is what you're getting for free by doing almost nothing. By flipping a coin, not even looking at the formula, you'll get 7/8. The deterministic algorithm is a little more subtle, but there's strong connections. Okay, so it's saying that for SAT, you can't do better than flipping coins. It's as if there's no structure, there's no information you can get out of it in any meaningful worst case kind of way. Yeah. So we do talk about some of the techniques underlying the PCP theorem, and I think we might be able to prove that like getting 0.001 is NP hard or something. No, sorry, getting 0.99999 is NP hard. And then to get it all the way down to 7/8 requires more legwork. Yeah, this would be one of the most spectacular results in the 90s. This came out in the 90s and over the course of a decade. Yeah. So first they got some constant. Oh, there's some constant beyond which it's NP hard. That was already surprising. And then they were able to push it all the way down to 7/8. So I think in the randomized class, we kind of do enough to, at a high level, sketch some constant. And then getting down to 7/8, even I haven't really gone through that. Yeah. But some very nice techniques. So for example, the techniques and in fact the form of the theorem resembles, for example, error correcting codes. So do you guys know? Did I already give this speech? Okay, sometimes I rant. So you guys know how error correcting codes work? Or just zooming out. So Alice is talking to Bob. You send a message over a wire, and some bits get flipped, and you want to recover the message. So one silly thing you can do is like, oh, let's send the message 3 times. And then for each bit, like take the majority. Then you have to make 2 mistakes in order to get it wrong. Right? 2 bits have to get flipped. So that already helps. So the question is, so you're basically adding redundancy, but you want to do better than just copying and duplicating, right? So the field of error correcting codes gets these very lean codes that can recover from random bit flips, but with very little overhead. Okay. Now, what is this theorem saying? It's saying that if you can make fewer than 1/8% error, 1/8 fraction of error, you can recover an exact solution effectively, right? And what the proof is actually going to try to do is going to start with some 3-sat formula, and it's going to build a bigger 3-sat formula so that if you can do better than 7/8 on your auxiliary formula, you can recover an exact solution to your original formula. Okay? So it's going to have to build some redundancy in there, but you don't want the formula to get too big because you can't just blow things up, or else a polynomial time algorithm isn't a polynomial time algorithm, things like this. So you want to somehow build some redundancy into the formula so that it's sort of robust to a small amount of error in some very lean and efficient kind of way. Yeah, so there's all these kind of very interesting connections uh, in this area. Okay, that's just a little bit. Okay, but that's the PCP theorem. I think that without even knowing much about the techniques, just to prove the theorem statement is pretty cool. and worth pondering. So it's called a probabilistically checkable proof. Because at some level also, yeah, what's the context? Uh, if you're just trying to figure out if, okay, if you're looking at a formula in an assignment and you want to know if it's exactly true, you have to check everything. But if you want to know if it's like has 10%-ish error, then you can like, I don't know, randomly sample 10 clauses and see if one of them's wrong. That'll give you some information, right? But as soon as you have this margin for error, then you can do a relatively sparse amount of checking the assignment. Okay. So, so whereas we have these like provers or verifiers that run in polynomial time, in that world, you look at provers and verifiers that actually only look at a few bits of the proof, and with some constant probability of success, will verify it correctly, if that makes some kind of sense. But the idea is that Uh, yeah, so that's the idea. So is that you start looking at provers that can use randomness, but they might only need to look at a few bits to output with, 70% confidence that this is either right or wrong. But that means that instead of just having the normal certificate where you have to read everything through, you need to propose some other kind of certificate with redundancy built in. Yeah. Okay, good. It also tells you that randomization is fundamental because somehow this randomization is kind of going back to these very basic things like SAT. All right. Okay. So that's the approximate three SAT. The quicksort algorithm, I'm just going to present the algorithm first. We're going to do the analysis in the second pass. All right. So you guys know this problem really well. I give you n comparable elements. You want to sort them in increasing order. You know merge sort takes n log n. And you even know how to do the lower bound, if you remember. Yeah. You need n log n comparisons. Okay. So quicksort is a very silly algorithm. Okay, you're going to take n numbers. Your goal is to sort them. And maybe you already know this algorithm. So how does the algorithm work? Have you seen it before? I give you n numbers. I want to sort them. Let's pick a what? Yeah. So you first pick one of those numbers uniformly at random. Your goal is to divide it into two even piles. But of course, you haven't sorted it yet, so you can't do that. But you're hoping that if you pick a random one, it'll come pretty close to the middle, and it'll kind of give you a reasonable split. Okay. So you pick a random one, and then you say, oh, here's all the numbers bigger than the number I picked. I'll sort them, and then I'll also recursively sort everything that's smaller. And if you're always getting two even piles, that would be great. Issues you might not always, but we'll figure out how to analyze that. So as a picture, it's sort of like a randomized divide and conquer. It's arguably more intuitive than merge sort. Um, so you pick a random pivot out of your big array, and you use that to split your array into two parts. So these two parts haven't been sorted yet. You just know they're bigger and they're smaller, and then you recurse. Okay, so it's like recurse, the code is very simple. Okay, good. So we are going to prove first that it's going to get n log n in expectation on average. Okay. But if we have time, we'll also prove that it gets n log n with really, really high probability. Okay. So maybe like the probability that the running time is bigger than some constant times n log n, is at most n to the negative that constant over 4 or something. I don't know. Okay. But the point is that because n's big and it's going, negative n squared, negative n cubed, negative n to the fourth, so it's going to zero really fast. Okay, so you're almost always going to always witness n log n on an instance by instance basis for any large enough n where you'd even bother tracking the running time. Yeah, good. If we don't get to there, that's fine. Okay. And then lastly, I want to describe this quick select algorithm. And the idea being we'll have let you guys duke it out during the homework. Okay. So again, this problem you guys remember. Now I give you n elements. They're not sorted, but they are comparable. You want to find, say, the median or the rank 10, the 20th biggest. The obvious approach is to sort and then pick it out. But as you know, you can do better. We have that very clever median of medians algorithm, which is this divide and conquer thingy. Okay. All right. Here's a even simpler algorithm. It looks a lot like quicksort. So the first step, you're given your array, you pick your random pivot, okay? And you split the elements into two parts. It may not be as equal as it looks here. And then based on that, you say, oh, so this one element, its rank. Oh, it was a median. Oh, it was rank 100, rank 200. So you know which side to look for the thing you want. And so you're going to recurse on the appropriate side and get the element you're looking for. Okay. The intuition's kind of clear. You're hoping you split the input in half, in which case your running time would look like n plus n half plus n fourth plus n eighth and so forth, and you get n overall. But of course, that may not always be the case. Okay, good. There's no point in doing the pseudocode. It's obvious. So you're going to show that this will take linear time and expectation. And as I understand, this is much faster than median of medians in practice. Yeah. Why doesn't it automatically uh, mean that it's with high probability? I don't know. Well, maybe I didn't really strongly define uh, with high probability, but it can be n log n, a 1 over log n fraction of the time, right? So like n log n wouldn't be a very impressive running time. And if you're just working out the average, if it's like n log n for a log n fraction of the time, and then it's n for the 1 minus 1 over log n fraction of the time, it will still look like 2n on average. And to say that something, is bad is good 1 minus 1 over. So log n we don't count as high probability. We want it to be, polynomially small in n. That's the idea. All right. Getting the expected running time is usually the most important thing. All right, so here comes the definition portion. But again, I'm just not totally sure of everyone's background, or maybe you've done it but just haven't been refreshed, and that's totally fine. If this goes too slow, do something like do protest, order a Domino's pizza or something, to let me know as politely as possible that we should go faster. But obviously, I can't skip this if we're not. Okay, so all right, so have you guys seen this movie? No, oh yeah, you've seen the movies. Oh no, you saw the good one, huh? No Country for Dead Men, the sequel. No Country for Old Men. Yeah, so this psychopath goes around and he's asked the person that he might murder to call heads or tails, and if they guess wrong, they die. Okay. And what was that line? It's like, what's the most you've ever lost on a coin toss? That's the line in the movie. Yeah, what's the most you've ever lost on a coin toss? You wonder as you take your final. Okay. Okay. So if I asked you heads or tails, what would you say? Okay. Well, sure. But at some level, you don't know, right? The whole point is the outcome is uncertain. Okay. But you do have a sense that half the time it comes up heads, right? That's something. If how often does it come up heads? You say half the time. But like if you scrutinize that phrase, it doesn't make a lot of sense. What do you mean half the time? There's going to be one coin, one outcome, right? So, but when we kind of comfortably say half the time, we're already imagining like, oh, if I kind of simulated this over and over again and I laid it aside, I expect about half of the outcomes to be heads, half of the outcomes to be tails, right? But it's always been an exercise of imagination that I think we all intuitively understand. So, okay, so just some notational stuff. So probability theory, you have events. Events happen or they don't. And they're all assigned some kind of value between 0 and 1. Okay. Every event has like an opposite event, the event of it not occurring. And those two assigned probabilities always add up to 1. An event occurs or it doesn't occur. Sounds boring, but somehow if you just lay down these rules and you just follow them, then later when you start working with it, you can get lots of interesting counterintuitive stuff. Okay, you can start combining events. You have two events, A and B. Say, okay, what's the event that they both occur? What's the event that A occurs but B doesn't? A doesn't occur, B does occur, so forth, right? You have four possible combinations. And they're mutually exclusive and they're exhaustive. So if you add up the probability that A and B both occur, A occurs not, you're going to add up to one. Okay? You've all seen this before? Y- No. Uh, I don't know what's going on there. Yeah, this will remain a mystery. Okay. Uh, all right. That's how I know you're paying attention. Okay. Now when event A occurs, either B occurs or doesn't occur. Okay. So that'll tell you that the probability of A occurring is equal to those two kind of joint probabilities together. Okay. What's down here? We also have conditional probabilities. So this will be what's the probability of B occurring given A? Okay. And that's going to be defined as the probability of A and B both occurring divided by the probability of A occurring. Okay. Um, good. One thing kind of neat is if you start dividing both sides by, up above by the probability of A, then you sort of have this like, nice thing where everything adds up to one. Conditional in A, either B occurs or it doesn't. And if I add up those two conditional probabilities, you get one. Okay. So you can kind of take these conditions where you're in these, uh, I think with some examples, this will become more intuitive. I'm just kind of running through definitions. Sure. Yeah, I don't know who gave this a name, but if you want, we can call it Josh's theorem. Okay. All right. Now, it's important to point out that probability of B happening, conditional A, is not the same as just a probability of B, right? If you know something happens, it can affect your expectations of other things. So, okay. If there was equal, then we would call them independent. And these are all kind of equivalent. You pick one and you start plugging into those previous formulas, you find they're all the same. Okay. But it's really important to keep track of what's independent and what's not. Because independent will make your life very easy. And when it's not, you have to be more clever. Okay. So, unions of events, uh, A or B, one of the two occurs. Uh, you can break that down to three mutually exclusive events, right? They both occur or one occurs for each of the possible choices. And if you do a little bit of rearranging, okay, uh, then you'll get something called the union bound. So say, oh, what's the probability of A occurring or B occurring? It's always less than equal to the probability of A occurring without worrying about B, plus the probability of B occurring without worrying about A. Okay? It's very simple, but you're going to find this thing to be super duper useful. It's super useful because it makes no assumptions on A and B. They can be dependent. And we're going to find ourselves in these situations where you're analyzing like a big algorithm, which is also depending on data. And weird things, who knows what could happen, right? We're trying to do some worst case analysis. So sometimes when you're looking at something very complicated, all you can do is a relatively simple tool like union bound to start separating things. Okay, so union bound will be very useful. All right. Was any, should I go faster? That pacing okay? Faster? Faster. Okay. All right. So besides the events, you have random variables. They're like events, but they take values. Like you roll a dice, 1, 2, 3, 4, 5, 6. Coin toss, heads or tails. Okay. You have two dice, then you have a joint distribution of two random variables. We could think of as one random variable, right? A random variable that takes two numbers as its output. Okay, so you have joint random variables, x and y. They might be jointly distributed. They might be independent. So in general, say, oh, I have two random variables, x, y, I'm looking at them jointly. It's not always true that, oh, the probability that x takes some value, y takes some value together is the same as looking at them in isolation. Okay. Sort of the usual independent dependent kind of thing. It's independent if that is true, right? If it's really two different dice, then knowing the outcome of one has no effect on the other. So you can calculate the probabilities more simply. Uh, but if x and a y were secretly modeling the same dice, then of course it's always correlated. If you knew the value of x, you knew the value of y because they're modeling the same dice. Okay, good. All right. So here's something important: expected value, also known as average. Okay. So the expected value of a random variable x is I'm going to sum up over all the outcomes, the probability of the outcome plus the outcome, probability of the outcome plus the outcome. Okay? It's average in any sense of the word that you probably understand, right? Average, yeah. No, it should be probability. I've been using these slides for years. I don't know if anyone pointed that out. Peter, what happened last year? Yeah, see? What's going on? Okay. All right. And it's like the first lecture of class, too. It's like before they fall asleep. Okay. All right, here's something that's ridiculously useful. Linear expectation. You're looking at the average of the sum of two random variables, which may, reflect something complicated, right? And you might try to tease apart, oh, if X happens, Y happens, it could be very painful. But linear expectation actually says that the average of the sum is the sum of the averages. Okay, it's not very hard to work out from the definition. You just go through it slowly. Okay, but this is going to be insanely useful because, like the union bound, it makes no assumptions on X and Y, and it just kind of lets you slice through complexity like a knife through butter. Okay. Good. Okay. Just like we had conditional probabilities, you can have conditional expected values. Here we have the right notation. Uh, so the expected value of X conditional in A is going to be like before, except all the probabilities are conditional in A. Okay. And you have these nice formulas like, oh, if I want to figure out the expected value of X and I have some event A, I could break it down into what's the expectation conditional in A times the probability of A, plus the expectation of X conditional in not A times the probability of not A. Okay, so do I have an example here? No, okay. All right. Um, you can have expectations over multiple random variables, and then you can actually iterate the expectations. So if you look at the second line here, we start with what's the expected value of f of xy, it's some mysterious function f over x and y. But you can do, okay, what's the expected value over x? And then inside, what's the expected value f of xy over y, but conditional on x? Okay, so I guess here's some example I found on the internet that they found useful, or someone found useful. Wait, maybe it's not there. Oh, okay, here's the example. So I guess you're looking at the weather, um, and you have a random variable x if it rains tomorrow, and a random variable y if it rains today. You want to know if it rains tomorrow, given what you know today, right? So the expected value of x given y is what's the probability that it rains tomorrow, conditional on whether it's raining today. And if you know the probability that it rains today, and you know that the probability of it raining tomorrow, if it rained today, then you can start working out what's the probability it's going to rain tomorrow. Okay? I don't know if it's a great example, but it's the first one that comes up on Google. Okay, good. One last thing to shove down your throats. It's called Markov's inequality. It looks the most analytical, but it's totally reasonable. Okay, so this wasn't the case this semester, uh, but suppose our midterm average was like 40. Okay, what fraction of the class could have gotten at least 80% on the exam? All you know is that the average was 40. What Less than half, because once you have more than half of the class getting 80%, that alone brings the average above 40. Half is the max. That means that would also mean everyone else got. Yeah. Okay, and that's all this is saying. Okay. Maybe another way to to put that. If you looked at this version up here, the probability of getting, so if x is a non-negative random variable, it needs to be non-negative. The probability of getting twice the average is at most 1/2. The probability of getting 4 times the average is at most 1/4. It's totally common sense. You can break it out and prove it by expanding out the definitions. Uh, yeah, there's nothing to it. Okay, good. Is there a proof here? Yeah, so this is just breaking out like the conditional expectations, and then you just drop this term. Okay. No need to look too closely. I think you could do this on your own if you wanted. Okay, good. All right, good. We're done with the dry part in record time, I think. So sorry for that. Uh, okay. But if you have any questions, it's a great time to address it because obviously, if any of the definitions went too fast, it'll make it a little tougher to understand what follows. All right, good. I think each subsequent year, everyone gets better at probability because it's such a big theme in machine learning. All right, so let's go back to approximating 3-sat. So here we had the silly algorithm. Okay, we just flip a coin for all the random variables. Uh, and I want to try to prove that it gets 7/8. And the question is how. Okay, so this isn't too slow, but we'll see. We'll start small. Okay, suppose your formula had one clause. What is the expected number of clauses you expect to satisfy? Yeah, because in particular, for this one clause, what are the odds we satisfy it and what are the odds we don't? Because, yeah, so in this case, you would need like tails, tails, heads, right? So there's a 1 in 8 chance of getting it wrong. So the probability of E1 is equal to 7/8, and that'll get your expected value. Good. All right. What about two clauses? In this case, there's no variables in common in these two clauses. 1, 2, 3, 4, 5, 6. How would I analyze this? Like, what's the probability of E1? What's the probability that we satisfy both 7/8? So this will come from the previous exercise. Okay. But in our definition of expectation, it's more like, oh, what's the probability of 1 times getting 1 times 1 and probability of getting 2 times 2. So that means we need to start looking at, okay, what's the probability of E1 and E2? Sorry? Yeah, yeah, so in this case, the underlying variables are all disjoint. So it's independent, and you just get 7/8 squared, right? And same with like probability E1, not E2, you're going to get like 7/8 times 1/8 or something. And then the last one, I mean, I'm skipping one that's sort of symmetric. This will be like 1/8 squared, although you can ignore it because it gets you 0 points. So that means your overall expected number of clauses, right, it's going to look like 2 times 7/8 squared. No, sorry, I lied. Yeah, no, I didn't lie. Plus 1 times, there's E1 not E2 and E2 not E1. 2 times 7/8 times 1/8. Okay, what is this? The first factor of 2 is if I get both, I get 2 points. So this is 2 points. And the second one is I get 1 point, but there's two ways to do it. E1, not E2, or and then each of those occur was probably 7/8 times 1/8. All right. Anyone do the mental math? Sorry? 7/4. Okay. 7/4. Okay. Good. All right. Now what happens if there's one variable in common? Before it was easier because they're independent. How would I analyze it if that has one variable in common? Okay, so now I can say, okay, if x3 is equal to true, then you just get 2 points. So now we need to look at like, oh, what's the expected number of clauses conditional on x3 is equal to false? And now I guess what remains is independent with two variables each. So you'll probably get something like 2 times 1/4 plus 1 times 2 times 1/4 again. Something like this. What would this be? 1/2 plus 1/2 is 1. Okay, so now you're getting something like, so you have your expected number of clauses, and we'll write that as, okay, 1/2 chance it turns up heads. So expected number of clauses conditional on x3 to be true, plus 1/2 the expected number of clauses, x3 is false. If it's true, you just get 2 points because both clauses are satisfied right away. So 1/2 times 2 plus 1/2 times 1. So what do you get? Did I do that right? Sorry. So you get a 1/4 chance of getting both. Oh, this is 3/4. This is 3/4, isn't it? Okay, sorry. And then this would be 1/4 times 3/4. 3/4 squared, and then this should be 1/4 times 3/4. Okay, so I'm just making stuff up. All right, what does this come out to? 3/2? You have the expression on your face, like, it might be 3/2. Anyone else get 3/2? Yeah? Okay. So then I go down here and I do 1/2 times 3/2. Okay, so that's conditioning on x3 equals true, you get 2 points. Or x2 is equal to false, you expect to get 3/2. Okay. And so what do you get? 7/4. Okay. All right, but it's getting messier, right? All right, now suppose I gave you three clauses. Okay, good. So the point is that when you're looking at a full formula, right, what gets complicated is you have all these variables interacting with each other, the clauses are interacting with each other, and that was only like two or three. If you try to analyze it directly, it's already painful. Okay, so, but this is the basic question at play, which is in general, how are you going to analyze some kind of randomized mechanism where there's some like combinatorial explosion of possibilities, right? It's not just that. This will happen in sorting. It'll happen in all of our algorithms where a gazillion different things can happen. And to map them out is impossible, right? So, okay. So the big idea is that we only want the average. And the average doesn't require mapping out all outcomes. You're just outputting one number. Okay, so things can potentially be much simpler. So just realizing that you're looking for the average and that's much more tractable is just as important as the calculations we're about to do. Okay, good. So what we're going to do is we're going to make a random variable for every clause, yi. It'll be 1 if it's satisfied and 0 if it's not. So the sum of yi's will give me the number of clauses that are satisfied. So they're not independent random variables. One clause is satisfied, the next one is more likely or less likely to be satisfied. But for a particular clause, what's the expected value? 7/8. Good. All right, good. Now, let's look at the expected number of clauses satisfied. That's what we wanted, right? Okay, so we can write that out like this. All right, now what do we do next? Okay, linear of expectation. The expectation of the sum is the sum of expectations. And this is very easy to analyze. Okay, starting with M. Okay, so maybe this is a little bit of an easy example as our first example. But when you look at things the wrong way, it can be very hard. When you look at things the right way, it can be very easy. Okay, so linear expectation does a lot of work for us. And really the word average is doing a lot of work for us. Okay, good. All right, so that's how you get the 7/8 approximation on average. Now we're going to make this a deterministic algorithm, which should be surprising because I couldn't imagine a more random algorithm. Okay, good. All right. Well, here's sort of our setup. But maybe I should first ask, does anyone have any ideas? Yeah, better to show this. Any ideas for making a deterministic 7/8 approximation for 3 set? Yeah. Well, we talk about the clauses having 7/8 chance, as opposed to the x's having a 7/8 chance. So one way to think about this is, can we get a deterministic algorithm that gets you just an average outcome of an experiment? Yeah. So how would you pick x1 basically? Right? You have to make some decision first. So you're going to set it to be true or false and based on what criterion? Like a greedy heuristic, which is better? Yeah. That won't quite work, but that seems more sensible probably than what we'll end up doing. Yeah. Yeah. Well, that would correspond very much to just picking which true or false based on which ones it immediately satisfies more of. You're trying to get more ones than 3/4. Is that just saying, does it appear more as x1 or more as not x1? In what sense? Okay, so let's tease this out. I think we're going in the right direction here. Okay, so I'm gonna let z be a stand-in for the sum of yi's, number of clauses that are satisfied. And let's just look at something like this. The expected value of z, right? And you're trying to choose x1. Okay? But you could ask, if I chose x1 to be true, how will the rest of the experiment look? Or if I set x1 to be false, how would the rest of the experiment look? Okay? So this is just simple conditional probabilities, right? The expected value of z is half of the expected value of z given I set it to be true, and half of the expected value of z given I set it to be false. Okay? How can I try to use this to decide on what to choose x1? Yeah. So one of those conditional prob expectations are at least as good as the original expectation. They can't both be worse because the expectation is the average. So one of those choices are good. Okay, so there's some choice that'll maintain your average, and you can keep finding that choice, then you'll be able to get there. Okay, so the question is, how do you decide which one? Well, maybe another question is, how do you compute it? So if you can figure out the values of z given x1 equals true and z given x1 equals false. Yeah, I mean, it's a little bit more careful, but like if you start expanding this out, right? And then you start looking at all the clauses individually. If I set this to be true, what are the odds that it continues to be satisfied? And then that's going to be like, well, okay, if it's in the clause, then maybe it becomes uh, 1 right away automatically. If it's not in the clause, it's still 7/8. If it's in the clause, but it's negated, then it goes down to 3/4, you know? But it's easy to look at all the clauses on a one by one basis and get exactly this number. So it's easy to calculate. You can do it in one pass. So you can just compute which choice is better. You just write a loop and you do some arithmetic. Good. So that gives you a whole algorithm. Now you've chosen 10 variables, and the expectation, if you randomly flipped all the remaining variables, is still good. Now you're on to variable 11. I'll compute the conditional expectations and figure out if I should set variable 11 to be true or false. Then variable 12, true or false, all the way down. And you always maintain that average. You might get better, but you always maintain that average. Okay, so yeah, nothing, what's going on here? Right, so you just break it down into two conditions. One of these must be good, right? So this is called the method of conditional expectation. So a lot of these algorithms that have good expectation, you can do this trick and turn into a deterministic algorithm, okay? Just by figuring out how each choice influences the average. Okay, good. Any questions? That's the algorithm. Yeah. Well, it's a deterministic algorithm, so it's going to be 7/8 with very, very, very high probability. Huh? Well, I think something like quicksort or quick select. We're about to discuss it, but I think maybe a key point is that here, the fact that you can actually calculate this value is very useful. Maybe we keep an eye out for it. So maybe we'll go through quicksort and then we'll think about whether we could have de-randomized it. Quicksort has slightly different considerations because there's so much emphasis on speed, right? So the question is whether you can calculate these things very quickly. Okay, good. Quicksort. All right, so that's our randomized divide and conquer algorithm. Pick a random number, split up the remaining numbers, and recurse. All right, so if we try to model this recursively, what might I write? T of n is equal to yeah, that would be like the set. Well, I'm trying to write the math part. What'd you say? Oh, so ideally 2tn over 2, but your pivot may not actually split the input in half. So it might look something more like t of k minus 1 plus t of n minus k plus big O of n, where k is chosen uniformly at random. Yeah. So, okay. Yeah. So what's the best case? Splits in half. So ideally, you're always splitting in half. And then you would just get the usual Tn over 2 stuff that we're used to. Okay, and if you design this algorithm, maybe that's intuitively what you have in mind. Well, of course, that might not be the case. What's the worst possible thing? Yeah, so something like t of n is equal to, say, t of 1 plus t of n minus 2 or something. Actually, you can do worse. I could put 0 and n minus 1 plus on. So you keep choosing the first one, the first one, the first one, and you're making no progress, but you have to look at the whole array every time. How long would that take you? That would be n squared. Okay, so it's certainly within the realm of possibility that this algorithm is slow. It takes n squared time. It ends up comparing everyone to everyone. Okay, so this is sort of a conceptual question. We have this kind of best case, ideal case we have in mind of n log n. Uh, but in a certain strict sense of the word worst case, it is possible to get n squared. Okay? And also, there's some question of like, okay, this algorithm seems kind of complicated because compared to the 3-sat thing, it seems more adaptive. You pick one pivot and you pick more pivots and recur. But if your first pivot is good in the middle, but then your pivots later on are bad, how is that different from if the first pivot's really bad and then middle pivot's good and stuff, right? So there seems to be some path dependency that's like gives you a headache if you think about it. Right? So the question is sort of how do we untie ourselves from this knot? Yeah. All right, so good. So here again, average is going to do a lot of work for us. It's going to do all the work for us. So we're going to ask what's the expected running time, which is sort of like saying, oh, for every possible running time, I add that number times the probability of getting it. Okay, but what's the average running time? That's just a definition. All right, so good, good. All right, so first, any ideas for how to analyze the expected running time? I should give you guys a chance. Yeah. Okay, so maybe you're imagining something like, oh, can I start putting like expected value around this, like this, and then start doing stuff that are like, conditional and varied values of k, and do some fine-grained analysis on the k, stuff like this. Okay, but you imagine that might be a little painful to dissect. You can push that. We're going to take a different approach, which I think is very slick. Okay. So what we're going to do is focus on the number of comparisons. So I can just count the number of comparisons in the algorithm. That'll give me an estimate for how long the algorithm takes. It's basically just comparing. Okay. So what I'm going to do is for every pair of random of elements in their ranked order, the 10th element in sorted order and the 20th element in sorted order, I'll make a random variable that's 1 if they ever get compared and 0 if they're not. Okay, so for every ij, I have this variable xij, just indicating if the ith and jth element in order got compared. Okay, if I can count those up, then we're in good shape. Okay, there should be something here. That's right. So the sum is the total number of comparisons. Good. Good. So we want to analyze this, the expected number of comparisons as a proxy for the expected running time. Okay. But we haven't done anything yet. We're still looking at a big, complicated algorithm. So all those weird dependencies. So what should we do next? Split it up? How? Linear of expectation. Okay. Often in this class, if you see an opportunity to use a linear of expectation, just take it. Okay. So now if you look at the right-hand side, I'm summing over all pairs. Say what's the expected value of this random variable. That already looks simpler, right? Because in particular, I can analyze each pair ij in isolation. In actuality, they're not in isolation. Whether one pair gets compared strongly influences whether another pair gets compared, right? The algorithm's complicated. Like the things it can do are complicated, but the analysis simplifies because of linear expectation. Okay, good. So we just have to analyze one of these. All right. Any ideas of how? Yeah. Yeah. So let's see if I have a picture. Okay. So first of all, since it's a 0, 1 random variable, we're just asking what are the odds that they get compared. Okay. So you have some array and I and j is somewhere in there, right? There's some elements also to the left and some elements to the right. And what I'm looking for is some kind of sentence that really captures when and why and where, something related to the pivot I and j get compared. Yeah. They only get compared if either one of them is selected. Any of the other. So that's like 2 out of n. Okay, so let's say that I pick a pivot in the middle between I and j, then they'll get split up and they'll never get compared. What if I pick a pivot to the left? Well, it's sort of like the game gets pushed to the next round, right? Or if I pick an element on the right, bigger than j, we don't know yet if they'll get compared. We'll find out later. Okay, so in particular, I and j are going to get compared if and only if I or j is picked as a pivot before anyone in the middle. We don't have to worry about anyone on the outside. So if I and j are very close, they're actually more likely to get picked. If they're really far apart, they're less likely to get compared. Okay, good. So they're compared only if I or j is picked as a pivot before anyone in the middle. I'm actually not worried about anyone on the outside. Okay, and what are the odds of that? Because, yeah, perfect. So it might be a little confusing to think about because you pick pivots dynamically and stuff like this. But still, at the end of the day, any of those numbers amongst themselves are equally likely to be picked first, because each round is a fair game. Okay? So without having to worry about when exactly down the recursive tree it got picked, you can still say with confidence that they're all equally likely to get picked first. Okay, good. So, right, we have something like this. Okay. So they'll get compared only if it's picked as a pivot before anyone in between. That happens with probability 2 over j minus I plus 1. The plus 1 is some fence post thingy. Okay, good. So now let's go back to analyzing the expected running time. We have these random variables set up. The sum is what we're trying to bound, an expectation. You apply linear expectation, and we plug in what we just did. Okay. So I just plugged in the thing. It looks kind of messy because there's two sums, but it's really just summing over all the ij's. Okay. Here, at least when I do it, I find it best to interchange the sum. So now I'm going from j goes 1 to n, and I should go from 1 to j. Possibly j minus 1, but it's not a big deal between friends. Okay. And now what does this term add up to? What does this term look like? Yeah, so if you just enumerate the terms, like in order of I, you have 2 over j, plus 2 over j minus 1, plus 2 over j minus 2, all the way down to 2 over 1. Okay. So you have something that looks like this, and this is the nth harmonic number. Does anyone know how to prove this? Or easy, quick, yeah. Yeah. So one way to always remember how to do this is that this sum is a whole lot like from 1 to say n plus 1, right? Because if you kind of drew this curve, then this sum is sort of like the Riemann sums underneath. Okay? And then if you integrate that, you get log, as you've done a million times in high school. Okay, it's an easy way to remember. Integrating is often one solution to those, one way to get solutions to these sums. Okay. All right, good. We're doing great. All right, so we showed that it takes n log n time on average. Maybe I should just take a moment to absorb what we did, though. This linear expectation trick made our lives way easier. Yeah, it took a potentially very complicated dynamic algorithm and just completely flattened it out. You're not at all worried about like the interdependencies anymore. Good. All right, so let's do something new. Let's try to show this will take n log n, at most n log n with high probability. I never really defined high probability, but it'll be clear by the end what I mean. Okay, so this one is a little bit more subtle. Okay. Okay, so let's say that a subproblem involving, so as the algorithm evolves, you get all these subproblems until like there's one element left and it's dead. And there's no subproblems anymore. Okay. And so for each element, I can say, oh, how many subproblems did it appear in before it kind of fully resolved itself, which is how many recursive calls. And it was each of those recursive calls that gets compared to the pivot. So for each element, I count, oh, how many subproblems it appeared in, and I sum them up. That'll give me the total number of comparisons. It's just being accounted for differently. Okay, so we're going to focus on that this time. And here's the claim. Okay, the claim is that for every element, the odds that it appears in, I don't know, 32 times log n subproblems is at most 1 over n cubed. Okay. I think I chose like big generous numbers to make life easy. And you'll see from the analysis, if we made the 32 bigger, the n cube would go down. Make it 64, and n cube becomes n to the 6 or something, I don't know. Okay, so, right, good. So that's what we're going to show. Each element only appears in a certain number of subproblems. Why is that useful? Okay, so what I ultimately want to show is that, let me go through this slowly. So I really want to show that for all elements simultaneously, they're appearing in at most log n subproblems, 32 times log n. Right now, you know that with each probability, any particular element will appear in at most 32 log n. Okay. But here, what we can do, and I should have erased this and let you guys guess. So what's hard is to try to analyze all the elements together. What's easy is to analyze all the elements apart. So if you apply the union bound, okay, so the first one is asking what is the probability that any of the elements appears in at least 32 log n subproblems? And the second sum is, let me sum up over all the elements, the odds that it appears in 32 log n, too many subproblems. Okay. And 1 over n cubed is so small that if you have n of these terms, you still get 1 over n squared. Okay, so they're all so individually small that this union bound, which sometimes seems weak, is not a big deal. Okay. So then just by figuring out how to analyze one of these, you're able to get all of them simultaneously. You lose a factor of n, but that's no big deal at this point. Okay, good. So, like before, we've now reduced to the setting where we can focus on one element at a time. Yeah, okay, good. Okay, so if we can show that each element only appears in about log n subproblems, that'll give you your n log n running time. Okay, it was probably error at most 1 over n squared. Okay, good. All right, so now we just have to focus on one problem. Let me parse through this slowly. Unfortunately, yeah, uh, I talked to Paul Valiant for a while. and I kind of ran out of time doing a good job erasing everything. All right, so um, okay, so I'm going to fix an element E, right? And I'm just going to focus on analyzing this one element E. Okay, and to that end, I'm going to introduce more random variables. So for each integer I, like I equals 5, we'll say, okay, how many elements are in the same subproblem as E in the fifth recursive call, in level 5 on the recursive tree, level 6, level 7, level 8. And if it's done, like E is already selected and it's kind of established, then we'll call that 0. Okay? So that means that our DE, the number of subproblems E is involved in, is going to be at least 10, only if in the 10th problem there's at least one element in that subproblem. It seems a little artificial, but it's to set up an analysis, right? We're trying to analyze something clever, so we need to, do some funny stuff. Okay. All right. So our goal is to upper bound this term. I want to show that by the time, I is 10 log n, this expectation is super small. Like there should be 0 elements left. Okay? Which is sort of saying, it should be over. Yeah. Feel free to ask questions because I feel like it got a little more notation heavy all of a sudden. Which, if you do this a lot, then it's not a big deal, but the first couple of times it's, yeah. And I can see from your expressions that, okay, good. All right, so how I'm going to analyze this. So first I'm going to say that a pivot is good if it does roughly what we expect. It's in one of the middle half of elements, yeah? No, so DE will ultimately be, DE will be the max I such that xi is greater than or equal to 1. That's like a kind of the contrapause or something related to this statement. Okay. Yeah, so once there's no more elements left in E's subproblem, it's done. Okay? And this seems, so what's going on is we really want to analyze DE. Okay, this often happens, is that we can't analyze the thing we want directly because it has to be mathematically proven, right? So sometimes you have to do these funny things and introduce these funny definitions because there's like a very limited number of things we can do mathematically. Okay, so maybe we'll reflect on that in a moment. So that's why we're introducing these xi's. We're going to find these xi's to be a little bit easier to analyze directly. And then based on our understanding of xi's, we'll be able to infer something about DE. It's a little bit roundabout. Okay, but this kind of style happens a lot. The payoff is good because the algorithm is very simple and it works great. Right? This is sort of what you want. You want to give your computer a simple algorithm, and then you'll do a little bit of complicated, clever analysis once, and the algorithm will benefit forever. Okay, good. So onwards we go. We'll finish in a minute or two. Okay, I'm going to call pivot good if it falls in the middle half. So there's k elements left, and it's in one of the middle k over 2. So there's k over 4 on the left, k over 4 on the right, somewhere in the middle. Okay, so it's kind of doing what we expect. And whenever you have a good pivot, you're going to get rid of at least 25% of the elements in your subproblem. Okay, good. So, all right, so given that, what is the expected value of x1, the first subproblem? This is not a trick question. We're going to analyze each of the xi's. So the first subproblem, how many elements do you expect to have in that subproblem? N. So that's just your starting point. Oh, yeah, okay. Maybe x0 is n. Okay. So we'll work through x1. Okay. So I want to upper bound this by something. I want to do some less than equal to. So if you have a good pivot in ya, A 1/2 on the right. Uh, right now we're just breaking down the conditions. So I forgot the 1/2 on the right. Yeah, yeah. Okay. So if it's a good pivot, how big can x1 be? 3/4 n. And if it's a bad pivot, what's an easy upper bound? N. So we'll do something like that. Just doing something lazy obviously could be much better, but I won't even worry about that. Probably 1/2, you get 3/4 n left. Probably 1/2 all n is still there. But an average is like 7/8 n. Okay. Now if you go to other values of xi, right? So let's say that you're worrying about round 100, but you're going to conditional on round 99. Okay. And we do the same calculation as before. Okay, so conditioning on xi minus 1, so that's just a fixed value now. And you're going to get, on average, 7/8 of whatever was there before. So exact same calculation. Okay. So now, when you start looking, the claim is that in the 10th round, the expected number of elements is 7/8 to the 10th times n, right? So what's the base case? The base case is just x0 equals n, nothing exciting. All right, in the general case, what's the expected number of elements in the ith round? Okay. And here what we can do is iterative expectations. Okay. So what's the expected value of xi? Conditional on xi minus 1, because that's what we know how to analyze. Okay. That'll be 7/8 xi minus 1. And now you can use induction. So you get something like this. Okay. So it seems a little exotic, but once you have something like this, then I keep doing that. Once you make k big enough, then what does this start to look like? Just do it. Something like 1 minus 1 over 8 to the k. How do you deal with this? There's one inequality that's like super duper useful. It's like the most useful inequality in the world. Huh? Bernoulli's inequality? First of all, it might have a name that I don't know. Okay, what is it? Okay, I heard less than equal and greater, so I think there's some confusion. Okay, I'll give you another one. It's so you guys know that e to the x is equal to 1 plus x squared over 2 plus, okay? So this inequality holds for all x positive or negative. 1 plus x is less than equal to e to the x. Okay, so if you draw the exponential curve, this function will go underneath. Okay, that's obvious when x is positive from the Taylor expansion, but it's also true when x is negative. You can just like take the derivative of 0 and see that it's kind of decreasing faster. Huh? Oh, was there simpler? I don't know. So once you have that, you just can put the k in the corner. Okay, and I chose k to be like 32 so that things start canceling out. You know, negative 4 log n times n, and you get 1 over n cubed. Okay, so the expected value of the 100 log nth value is so low, it's basically 0, right? In fact, this is smaller than 0, which is impossible. I mean, smaller than 1, it has to be 0. Okay, good. We're really close to finish. So how do I put the finishing touch on this? I'll let you guys take it home. So ultimately, I want to show that by, round 100 log n, I'm done. Okay, so here's one. Okay, so if you've survived 100 log n, that means there's at least one element left in problem 100 log n. Oh yeah, okay. And what's it called? Yeah, see, it makes you feel like a real teacher. Why is it what? Uh, well, first of all, I don't mind less than equal to. Um, I mean, it's basically equal. Oh, is it? Oh, do you want it equal? Okay, sure. I think it is equal. Uh, yeah, I think I'm just, saving calories. Okay. Right. So we use the thing in the bottom right corner, which was called Markov's inequality. Where did it go? Why didn't this work like I want? Oh, okay. Like that. So mean less than or equal to expected value of x cubed, xk, which is 1 over n cubed. Okay. So that's what we wanted, and now everything, goes back and that finishes the proof. Maybe the only comment I wanted to make, DE was the thing we wanted to analyze, and it made sense. How many rounds does E appear in before it's chosen as a pivot? If you can analyze that, you get the whole thing. But we had to do this weird detour through the xi's because that was the thing for which we could do some kind of analysis like this. Okay, it's just that we weren't able to directly estimate DE, so we did this roundabout thing to show that, oh, for sufficiently large k, xk is going to be 0 is, yeah, that's right. Yeah. Okay, so that's it. But now you guys have done a high probability analysis, which is pretty sophisticated. So that's not bad. Okay, so I think that's all we had today. And then on the homework, you'll get a chance to do something similar to the expected quicksort analysis when you analyze quick select. Yeah. Okay, sounds good. All right, see you guys next time.